Hi, welcome back to AP Examined, and in this lesson we'll be talking about continuity. Now, I've listed some of the important things that you'll have to know that my textbook covered in the section on continuity for limits. And so, if we make it through all of these, then you'll have a really good understanding of what's necessary to move on from limits and go on to derivatives and what continuity really is. So the first question is, what is continuity? Continuity is best seen. It's basically, can you take a function and draw it with a pencil without ever lifting it up? Now, that's not distinct mathematical terms, but if we have something like this, that's a continuous function because every point is touching the point right next to it. And I'll make a second example over here of a function in which it is not continuous. Some of the stuff we saw with limits involved open points where the function continued somewhere else, like that. Where we move along here, then go, once we hit there, we jump down here. Now, this function is not completely continuous because at this point, we keep going, but it doesn't continue here. We have to jump down, and this abrupt jump makes this not continuous at this point, because we had to lift up our pencil when we drew this graph. So this is our continuous function, and this is our discontinuous function. So the next concept that we have to cover is discontinuity. Or sorry, not discontinuity, one and two side continuity, whereas this is continuity and this is discontinuity. What does it mean for something to be continuous on one side or two sides? Now, when we're talking about sidedness to continuity, we're talking about specific points. You could say that, if we go back, we can say that any of the points along this function is continuous because you can go directly to the right or left with a pencil and get the point right next to it. So like this, if we pick a point here, our point up here is going to be continuous because we can go boom to the left or to the right. There's points immediately next to it. And so, because there's a point directly next to it on the left and the right, that's two-sided continuity. But we could have one-sided continuity when we have something like this on the left side, where when I drew this graph, you could assume that this goes on infinitely and that I just didn't draw it completely out. But if it ends here, if we draw a little barrier there, if it ends there and doesn't continue beyond this point, then it's only continuous from the right side, because you can go to the right with your pencil and start drawing along, or just one point next to it, but there's no point to the left. We can't draw with our pencil to go to the left. So that's one-sided continuity. And then it's one-sided continuity from the left on this side over here. Now, if we go here, we see that this point is the point's actually down here at this x value. Here it's continuous from one side on the right, which is clear from this graph. If we try to go to the left, we can't get to the next point with our pencil without lifting it up. So that makes it one-sided from the right. And if you pick the last point right before this open point there, that's continuous from the left, but to go one more point to the right and go down here, you have to lift up your pencil and put it back down there. So that's not continuous on two sides. And this point itself, we wouldn't call it continuous because it has to be, generally when we talk about a point being continuous, it has to be on both sides. So let's go check off some boxes here. We've covered what continuity is, what discontinuity is, and what it means to be one or two-sided continuity, to have that. Now, properties of continuous functions these are pretty simple, and probably what you would have assumed looking at continuous functions. But let's go ahead. If we say that, I'll set up two continuous functions here. So if we say we have something like this, and then another random curvy line like this, if you add two continuous functions, these are both continuous functions, assume that these go on infinitely in both directions. If you add any 2 points on them together, you'll get another continuous function. And sometimes we call it the composite function. So, say for example we took this point, we'd add here and here, and so this looks like it might end up around there, not exactly sure where, but then we go 1 point over from here and here, and we get another point right next to it, and so on. And what we get would be just the morph of the two graphs, something a little more toned down. At the end here it'd probably curve up, as you see these are getting higher, but that's beyond the point. All you really have to know is that if you add two functions that are continuous, you'll get a new continuous function. The same goes for subtraction. The same goes for subtraction and multiplication. If we multiply these two together, at every point we'll get a new continuous function, as long as these two original functions are continuous. That goes for multiplication. And so if we multiply these two together, we get a continuous function. The same goes if we multiply by a constant factor. So if we multiply one of these by 5 or by 4, as long as the original function is continuous, we'll get a new continuous function. And the same goes for dividing these two. And so now let's get into wait a second there. Okay, sorry. So that's our properties of continuous functions. They behave just like you'd expect them to. And now the intermediate value theorem. This is something you're going to see a lot, but it's not too difficult. So we say that, okay, so the official way of describing the intermediate value theorem is to say that in a function, I'll give you a piece of the function right there. In a function between any given points a and b, all values between f of a and f of b are covered, or exist between a and b. Now, let's see what this means. If this is a, then f of a is going to be right there. Oh, that was a little sloppy. Let's make that again. So f of a. And then we go up here, and looks like right about there we'll get f of b. There we go. So what we're saying is, if we start at A and go to B and move along this curve, we'll touch every single point along this section here. So that if we say we can pick anything along here, and because this is continuous, we'll say boom, right there, there's a y value for that. And boom, here, there's a y value for that here, between these 2 points. And that makes sense, because if we're going from one lower x value in this example to a higher one somewhere, and you have to get there without lifting up your pencil, you're going to cross all these values to get up there. You're going to cross all these values. So there we have it. That's an intermediate value theorem. You probably won't get very many examples, many questions on the intermediate value theorem, but it's important to know because you might have a question about it on the AP or your teacher might want you to know it on the test or describe what it is. So just make sure you understand that concept and you'll be fine. Alright, see you in the next video. I believe it will be, let me just pull up my list here, tangent lines. So we'll come back with tangent lines and we'll be ready to move on. So thanks for watching.